Hi viewers, welcome to my class on mechanics of materials. In this class, I'll explain the different mechanical properties of materials. First, let us define the strength. Strength is the resistance offered by a material against failure. And we already know how to draw the stress strain diagram and seen the salient points. So yield strength is the strength when the material starts yielding. So that is a significant point where material starts yielding, and corresponding the stress is yield strength. It's a strength, yield strength of a material is a stress when the material starts yielding, and this is a important parameter in the design aspect, because we want to limit the stress in a material when it is loaded well below the yield stress, because yield point is considered as a failure for most applications. So you cannot load a material up to the yield point. So the stress in the material should be below the yield stress. So we use a factor of safety to limit the stress. Ultimate strength is the stress corresponding to the ultimate load. There is a maximum stress that can be encountered during tensile test. So ultimate strength is the maximum stress or maximum load material can withstand during a tensile test. Ultimate strength is the stress corresponding to ultimate load during the tensile test. Fracture strength or breaking strength is the stress when the specimen fails or fractures. At the point of failure, what is the stress? The stress at which the material fails or breaks, that is the fracture strength. So during nominal stress strain curve, you would have observed that fracture strength is less than the ultimate strength. So that is because we are plotting the nominal stress strain curve. True fracture strength is going to be greater than the ultimate strength, or it will be equal to ultimate strength. If a brittle material, ultimate strength and fracture strength are going to be same. Impact strength is the energy absorbed by a material before failure due to impact loading. When it is subjected to impact loading, the energy absorbed by the material is indicated by the impact strength. If more energy it can absorb before it fails, it will have more impact strength. It resists more impact loading. Hardness is another property. It's a surface property. It shows the resistance of a material against indentation or scratches. So it is usually measured using Brinell or Rockwell or Vickers hardness apparatus. So they are the apparatus used to measure the hardness of a material. So usually the measured values are expressed as hardness number, Brinell hardness number, Rockwell hardness number, or Vickers hardness number. So this number indicates the hardness of the surface. These hardness numbers differs for the same material, so they have a different standard. The numbers differ. That Brinell hardness number for a given material and Rockwell hardness number will be different. Resilience is the energy absorbed by a material up to the elastic limit when it is loaded. So up to the elastic limit, the energy absorbed by a material is known as resilience. I have shown the bar loaded by an axial force P. Now you can find out the resilience as energy absorbed. So what is it, energy absorbed? What is the work done on the material? Work done will be stored as internal energy. Now the load applied is P, and it is a gradually applied load. We start from 0. The load starts from 0 and it increases to P. So the average force acting on the material is half P, 0 plus P by 2 or half P. And the change in length that is, this load is acting through a length delta L. So the average load is 0 plus P by 2 into the load is acting through a distance delta L. So the average load into the distance through which the load acts will give the work done. So average load is P by 2 and the distance through which the load acts is delta L. So P by 2 into delta L, that is the work done, and that will be stored as internal energy, or it is energy absorbed by the material. So resilience is half into P into delta L, and delta L we know it is PL by AE. Okay, delta L, deformation of the material, is due to axial load is PL by AE for a uniform cross section, PL by AE. So you get P square L by 2AE, or if you multiply the numerator and denominator by A, so P square AL by A square 2E. So P square by A square, P by A is sigma, P square by A square is sigma square into AL by 2E. So sigma square by 2E into AL, or sigma square by 2E into area of cross section into length, that will give the volume of the bar. So sigma square by 2E into volume. So that is the energy absorbed by the material. That is the energy absorbed by the material when it is subjected to axial loading. So this is given by resilience. So resilience is sigma square by 2E into volume. Now proof resilience is a maximum energy absorbed by a material when it is loaded up to the elastic limit without creating permanent deformation. So up to the elastic limit when it is loaded, what is the maximum energy absorbed? Whereas resilience was the energy absorbed, it need not be an elastic limit, loading up to the elastic limit. So energy absorbed within the elastic limit, energy absorbed is resilience. Whereas proof resilience is the maximum energy absorbed when it is loaded up to the elastic limit. The maximum it can absorb is a proof resilience. So for proof resilience you can use sigma square by 2E into volume, but you have to substitute the yield stress, elastic limit and yield point. Usually the stress is taken as a yield stress. So proof resilience is sigma y square by 2E into volume. So in this if you substitute sigma y, yield stress, that will give the proof resilience or maximum energy that can be absorbed. So beyond sigma y, that is yield stress, the material undergoes plastic deformation. So that is the maximum energy that can be absorbed by the material within the elastic limit. So it is called proof resilience. The maximum energy absorbed by a material when it is loaded up to the elastic limit without creating permanent deformation. So proof resilience is sigma y square by 2 into volume when it has come to the yielding point. So beyond that, permanent deformation takes place, energy will not be stored in the material, it cannot be retained. So modulus of resilience is energy absorbed per unit volume up to the elastic limit. Modulus of resilience is the energy absorbed per unit volume up to the elastic limit. So proof resilience is sigma y square by 2 into volume divided by volume will give the modulus of resilience. So it is given by the area under the stress strain curve up to the elastic limit. So this area represents the modulus of resilience. How it represents the modulus of resilience we will see. Shaded area you can calculate as sigma y. This is sigma y, y-axis is sigma y, and this is a corresponding strain E. So area of this triangle is, it's almost like a triangle, so it's sigma y into E by 2, and E is strain is stress by Young's modulus, so sigma y by E, so sigma y square by 2E. So that is area of this triangle. So sigma y square by 2E which is also the modulus of resilience. So the modulus of resilience is represented by the area of this stress strain curve up to the elastic limit or a yield point. Toughness, it is a measure of resistance offered by a material against fracture. It is measured as energy absorbed by a material till the fracture point. So what is the energy, total energy absorbed by a material up to the fracture point? The energy absorbed per unit volume is known as modulus of toughness. So modulus of toughness is represented by the area under the stress strain diagram. The total stress strain diagram till the fracture point, that area is modulus of toughness, because it's energy absorbed per unit volume. We have already seen that modulus of resilience is this area, this yellow portion, that is up to the elastic limit. The energy absorbed per unit volume is modulus of resilience, that is given by this area, whereas modulus of toughness is energy absorbed per unit volume up to the fracture point. So that's total area will give the modulus of toughness. That's all for today. Thank you for watching.